lots of walking like us, trying all the doors to get in.
Oh, no.
You guys may want to see. Right.
Set up. Do you want to connect with the taxi?
Yeah, how big your speed? Frank, how you showed up?
Yeah, we have it. Shut up.
Here, half an hour ago. Okay.
It's a nice place. Just
Good joke. Is there a background? Do they have a projector? This one doesn't. We have a online people who is already coming.
well, maybe this is loose.
So I think she just talked. The hall said their system is broken.
Oh,
Yeah, but they should tell us early. But if it's broken, they cannot hold. But when do they come? That's a big joke. They have to come from the online. No, I think not the computer problem. The projector is wrong. But did you try to test it, right? But you need to let us know we're renting this room.
Yeah.
And we have a guest from California. We have a lot of people waiting. We do not know this group, and our team is here about an hour ago.
Sorry.
Yeah, maybe if we do Zoom, would this be okay?
Yeah, for people here.
Yeah. Because if there are people online, we cannot walk back and walk off.
Yeah.
Yeah, let's do Zoom then. So you set up a Zoom meeting, set up a profession, and so they can also connect to Zoom, and you use the Zoom to live broadcast. Would that be okay?
Yeah. So
You have a smaller room. We don't have a lot of people here. We can fit in a smaller room with a projector. So do you have other meetings in this room?
Yes, but
Yeah. I can create a link on the Zoom if someone has a link. Yeah. Inja, can you set up the Zoom meeting now?
we can go back and track if there's other.
But this makes me feel very embarrassed as a professor this time. One guest coming from Seattle. And then we will get informed this is going on.
Okay, I will start the Zoom session and then just let him join the Zoom and then
can we use the 260?
We're gonna go check. Yeah.
Okay. That room is available.
Is that having a projector?
Yeah, that one I believe so.
Yes.
One of the room upstairs.
Yeah, can we move to there?
We're gonna go check.
Also, how can he join? He needs to join to project. Yeah, so that's why we need to.
Yes.
So this occasionally
Yeah.
can connect.
Yeah, so
Let me try.
So, yeah, it's like the connection is not so stable.
just because. But so you people came very early. You did not see the problem.
It occasionally can connect.
So you thought it came.
Yeah, you thought, okay, can be connected. So it's just like the connection is not so stable.
It's about that. Something not wrong. So shall we go upstairs? So Christy, is it okay to go to 260? Did you find the key? But there is move the screen.
Do you have a
They can also do presentation.
We found a smaller room. Sorry about that.
Oh, that's okay. It's working.
Yeah, but we need to go together. Yeah.
adapter 是咱们的吗
Let's go to it.
Both. Both. We want to check if there's some adapters there that belongs to us.
No.
No? Oh, yes, it's there. 帮什么忙？等会儿把这一关，他应该还在结束时。
No, 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 no.
Okay.
Maybe someone can hold for me.
I can hold this.
Yeah, yeah, yeah.
You can take the one.
Hold it. So.
好，龙姐，而且我已经很帅。
Yeah, yeah, yeah. Okay, you go with your chair.
Be careful. Yeah.
I got it.
Yeah.
I got it.
All right, move all the chairs that way. And move the table, this one to the front. All right,
Where do you want the chairs?
we don't need. You professors will stand an hour.
Really
You apologize to Professor Ioannou
No, don't worry, we have the same problems as you see.
because he's our guest.
Don't worry. Okay.
All right, so.
So connected? So we need
Yeah.
to.
Yeah, we need an
Cable, where's
HDMI
the
cord.
HDMI?
HDMI.
You have to.
You see. You do.
You wouldn't.
Maybe we put a sign to that door, just people can read, they know where to find us.
我们要把这个音转个高。啊，这样啊。
Okay, cool.
All right. Wow, perfect.
Okay, cool.
And we don't need these things, right?
Thank you guys. Thank you. Okay.
Thank you.
So, that's the, ready?
I'm mute the mic.
Are you ready? Yeah, let's start. Good afternoon, everyone. I apologize for the delay. It's totally unexpected that the audio system was broken and we have to switch to a different room. But we have an old Chinese saying, a very good dinner worth waiting. So I'm pretty sure you will not be disappointed by waiting this long. Today is our great pleasure to have Professor Petros Ioannou, professor from University of Southern California, to be here to deliver our regional transportation seminar for the PACTRANS. The title is Control of Vehicles and Traffic for safety, mobility, and efficiency. Actually, this matches our center theme very, very well. Yeah, so I'm Yin-Han Wang. I'm professor and director at the Paxton Center. So let me briefly introduce our speaker, and then I will ask Patrick to take the floor. Professor Ioannou is a professor at the University of South.
Before I do that, I will, because a lot of people are young here, probably were not born when some of these activities started booming. So I want to give you, and you hear all these words about platooning and this and that, and what the hell is that, and how did it come? I will give a very brief explanation of how this idea of, instead of building concrete highways, which was the traditional way of getting more capacity, how we decided to shift into technology and intelligence. Okay? So if you take two vehicles and following each other with some inter-vehicle distance, and the first vehicle breaks down, the following vehicle would hit it if the initial space in between was too close. So let's start mapping that. Map the delta V square. Why the delta V square? Because the delta V square, which is the relative speed at the point of collision, you square that is a measure of the damage done to the vehicles. So if you plot the initial distance with the delta V square, you're going to get, in manual driving, you get this curve. So if you drive with a distance beyond this point, if this vehicle stops, you're going to be okay. If you put sensors on the vehicles and you act faster, you shift this, you make this curve discontinuous. Okay? And then you say, well, why don't we use sensors and technology so we can put vehicles closer together, and that will increase the capacity considerably, because capacity is proportional to 1 over the inter-vehicle distance. But some other smart people say, wait a minute, we can do much better than that. Why don't we put the vehicles 1 meter apart, and we're right here, so if they ever collide, the collision is so tiny, and there will not be any damage. And that gave birth to the idea of platooning, organize the vehicles in platoons with 1 meter apart, and that will increase the capacity by 4 times. 4 times, 8 times sometimes. Of course, this assumption is very naive because they assume all the collisions will stay in one direction. Nevertheless, in the 80s and early 90s, this got a lot of momentum. The federal government was supporting it. Everybody was getting excited. There was a big activity from UC Berkeley with the program of PATH. California Department of Transportation was the leader to organize things in a platoon and automate the vehicles and the highway. So remember, it was the whole system, designing the whole system. So from this, two approaches came up back in the 80s. One of them was full automation with platoons, no human involvement, high capacity due to platooning in closed space. The other approach was more conservative, was the evolutionary approach. As safety is important, we have to start from where we are and slowly building safety technologies and automation and get to the point that maybe we can do the one. Initially, this approach got a lot of attention, most of the attention. I was working in this area because I was interacting with Ford, and they told me don't touch this part because we are not going to do it. So I started working on this part, and we developed at the time the adaptive cruise control system that I talk about. But this is, so the government decided in 1997 to have north of San Diego an experiment of this platooning approach. And this is what the video of what you are seeing. I was in August of 1997. And sure, you can have a bunch of vehicles following each other, not 1 meter apart, but it was a demonstration. Strangely enough, the day after the demo, the whole system collapsed. No interest. Okay? So this platoon idea was kind of killed in San Diego, except a person in my group actually, which I alerted him to this problem because I knew from my own experience, did some tunnel experiments and measured the aerodynamic drag between vehicles. Found out that if you have a track with a big surface and you follow another track, you can reduce fuel consumption by 20% because of the reduction in aerodynamic drag. So this became a motivation for trucking industry. And trucking industry is still talking about platoons for two reasons. One, reduction in fuel consumption, and another idea was if you have, let's say, a platoon of two vehicles, the first vehicle is driven by a human, and the other one is electronic because they cannot find drivers. So they're still playing with that, and there's still companies talking about truck platoons. But you're not going to hear platoons for passenger vehicles unless you're a graduate student, right? In Paris. So there are people who keep mentioning, but it's not as serious. Then when we thought everything collapsed, DARPA came in and said, no, we're interested in a fully automated vehicles. And they have this DARPA challenge competition in Ontario, California, going from Ontario to Las Vegas. And whoever wins gets 1 million, the second year was 2 million. And here is one of these experiments. And you can understand why the military is interested in autonomous vehicles. You have UAVs now, you have autonomous tanks, you have autonomous boats, you have autonomous, so it was natural. So a lot of the first competition, nobody won. The second competition, I think there were a couple of winners, I don't even remember the names. But sure enough, you can have a vehicle, getting the GPS points, having a lot of sensors on the vehicle, and navigate this distance of, I think it was 200 miles in less than 10 hours. Okay, so that's possible. So, after the collapse of these automated highway systems, the whole program kind of shifted into two directions, which is still today. You have on this side the automotive industry, which is really interested about vehicle safety. And they follow what I described the evolutionary approach. You see a lot of gadgets. If you buy a new vehicle, you're going to have a lot of gadgets. Drive-by-wire, handbrake is replaced by electronic brake, you have collision warning device, you have automated emergency braking, adaptive cruise control, lane keeping, and so on. And Tesla has autopilots. A lot of vehicles began with autopilots, but there is one catch here. The driver is responsible. So you have all these automatic features, you have to hold the wheel and observe. On the other hand, you have the robotics cars here, with the DARPA, one example. Then Google came in, created way more, because you are interested in a lot of data. They realized that if I you take the whole, all the roads and everything, that's a lot of data, and there is a business. But then out of the blue, Uber and Lyft and Cruises from GM, they realized that if now I have taxis without a driver, I can become profitable, because 80% of the cost goes to the driver. And this, what is going on here, when you hear about San Francisco having robot taxis and things like that. Here, what is going on in this area, driven mainly by taxi services companies. And here, this is the automotive, that people like gadgets, and if they like and pay for it, people go, oh, you're going to have an autopilot on your vehicle. People get excited, it's like the old VCRs. You buy everything on the feature, but you only use a button to on and off. So, and then they defined these 5 levels of automation that they were defined back in the 90s, by the way. And right now we are in number 3. So the vehicle can have full automation, but the driver is in control. And then the taxi companies are interested in level 5, where the driver is a passenger. There is no driver, basically, is set together. So, on the one of the first automatic features was this adaptive cruise control, where there's a radar in front of the vehicle and you do vehicle following. That we did back, I worked on this design back in the early 90s. And much to my surprise, 5 years later, it became a commercial. Today it's almost in every new car you buy. And Greyhound was one of the first companies that bought the radar produced by a company called Borat in San Diego. And they started seeing that if you have these warning devices on the vehicle, you improve safety. And that's what started, and it's still propagated today. Then they added vision, because they realized that the radar has a narrow beam, you can miss pedestrians. Then they put multiple beams, but then you get false alarms. Then they decided you have to augment that with a video. So you have now all this fusion of different sensors, and most companies have it. Most cars have it. So here are the technologies that are existing in most cars, and all these technologies have a beneficial impact on safety that I talk about. It improves safety quite a bit because they augment the senses of the human instead of replacing them. They help you see things that you don't see. And we talk about the robo-taxis here, that they are still experimenting with offering paid rides in San Francisco, no driver, but then people reacted to this. They started putting a cone on the vehicle hood to disable it. Some people throw trash inside. You have a lot of non-technical problems to solve. So you call a robo-taxi, comes, you put Coke on the seats, you leave your trash of chips there, you get out, who's going to clean that? Then another person calls it now, goes, says, wait a minute, I'm not going to go into a trashy car, pay for it. So all these problems that has to do with human nature are coming into play. People don't know what to do. In addition, we do have safety data. In order to assess safety, you have to create this probability data. So you have to drive millions and millions of miles, and people are doing that, and they report it to DMV. But it seems that the emphasis in moving to people get more excited about self-driving cars instead of our emphasis being on safe driving cars. That's what we need, because automated vehicles, they're going to solve, in my opinion, the problem of the taxi services. They're not going to solve any other problem. They're not going to solve the traffic, because the traffic, we have too many vehicles. And if you're replacing the driver, you're not removing the vehicle is going to be there. It doesn't matter who drives. It's still going to be crowded. And people talk about, maybe people who cannot afford to buy a car, but this service is not going to be free. You still have to pay. And then people who are disabled or whatever, but if I'm a disabled person, I like a human to be there, to talk to. I don't want to talk to a machine. What is it going to do? I want a human to grab me, to hold me, to look at me, and so on. So there are a lot of issues about it, and we don't know where it goes. On the positive side, though, a lot of ports have become automated. A lot of ports are becoming automated because it's a controlled environment. And then there are other applications. I just pick up one from a small town in Greece, Trikala, where they developed this van, this little car, that goes in a loop. It goes 25 kilometers per hour, very slow. It knows, it already mapped the route. It's very simple, probably covers 2 or 3 miles, and it goes around, like in a downtown area. People get in and go out. That guarantees safety. It's unlikely to hit an unknown situation. So things like that, which are kind of controlled environments, automation will be very useful. We have applications. As I said, ports are an ideal case, starting with the port of Rotterdam, and now we have over 120 ports which are fully automated, working 24 hours. So let me go now to the control of vehicle safety. So I look at this problem and say, okay, I'm going to design an automatic vehicle following controller, which no matter what is going to guarantee safety. Okay? So how do we do that? So what we did, we create what is called all the requirements for vehicle following. So for vehicle following, depending on your characteristics, you have to keep a safe distance from the vehicle in front. Then, if you go around the curves, that's where all your sensors will fail. You go around a sharp curve, you don't know what is around the curve, right? Whether you have a video, whether you have a radar or a LiDAR, it's not unless you have communications. Communicate with the rocks also. So you're not gonna know. So what do you do as a human? You slow down. So when the obstacle becomes in your view, you have enough time to stop without colliding. So we have to take that into account also. We also have to take into account that the sensors around the curves is very likely to give us a false read. So you send an arrow beam here, you see this one, this, but there's nobody in the only vehicle on your way is this one here. So how do you distinguish? Of course you can use video, but video may not work all the time. Vision may not work. So you have to take that into account. Depending on the environment, depending on your condition, the condition of your sensors, what do? You slow down, like you do as a human. When the weather is bad, you just slow down. So what it does when you slow down, your reaction times that are required to avoid an accident increase. So you have enough time to detect and take action. So we take all these things into account. And again, going into the traffic lights, if the traffic light is green, if this and that, if you have vehicle to traffic light communications, we introduce all kind of technologies. But the method we came up with is what is called, we created these sets. So one set has to do with safety, you don't hit anything. The other one has to do with the regulations. You have to follow the traffic lights, you have to follow the stop signs and so on. And the other part here is not very clear, it says safe speed.
Oh, six.
You have to, your speed is a variable. So, and then your controller should make sure you are all inside the intersection of these three sets on the C of T. So how is that going to happen? And here is the overall structure of the system. We go down to the throttle and the brake, not just the kinematic model. Or on the higher level, you have all these blocks. The important part is the one we work is this one, dynamic safe set generation, because this set generate is not fixed, because the speed changes and the regulation may be the same or maybe they change. The safety will depend what kind of vehicle you have in front of you, an obstacle, and so on. And then, of course, is the control design. So here we create all these inequalities that define the region, the set, the safety set. And the student like abstraction, so they follow this theory of control barrier factions with contracts. You don't need it here, but they like to create some abstract theory that could apply in many other situations. But the significant part is this one here. You can see here, you create all these inequalities, or you create all these constraints, and you take the intersection. So your safe set, like I show in the circles, is the intersection of all these regions that they are time varying. They are moving around, and you have to monitor them and update them. Then your controller is, you have the nominal controller that you design assuming you have no constraints. There's nobody on the road. Okay? That's your nominal controller. Then what you do, the safe control, the one you actually apply, is the one that minimizes the distance between the actual control input and the nominal subject to being in the safety set. Okay? So in other words, this minimization guarantees mobility, and this guarantees, and the constraint guarantees safety. Because one way to guarantee safety is to switch off the car, right? Safe forever, right? But you don't want that, you want mobility. So you want want to be as close to a controller that provides mobility, subject to being in a safe region. Okay, that's the idea. And we try to apply this to an intersection where every vehicle who reaches the intersection has the right of way first, but every vehicle follows this safety constraint. Okay? And see what's going to happen, because that will help me introduce the next topic. Watch what is happening here. Okay? So the vehicles go, the demand increases, and what do you think you're going to get at the end? So every vehicle follows safety and is moving.
Congestion.
First come, first
Stop
served, right?
Yeah.
So
Stop sign.
eventually you're going to create congestion. So what does it tell you? To control congestion, it cannot be done by each vehicle. It has to be a system level. So I ask a student to take the same example and create a system approach with the same demand and the same intersection by predicting the trajectories of the vehicles and letting them go. And you can see they can run forever. So it shows the control on the vehicle level and the control on the higher level, in the system level. So you need both. You need to have the vehicle control level for safety and the system level controller for mobility. So now I said that about the control design. Let's go what we have today. What can we do about traffic in general? Okay. So basically, the traffic control system now, if you took a course in controls, is operate like an open loop system. You don't know what's happening. There are metering. It measures the occupancy at a certain distance and creates the ramp. And when it's too congested, it switches it off anyway. The traffic lights look at a certain distance how many vehicles are there. It's all ad hoc, and there is no really much feedback going on. So what I mean, feedback, you measure the characteristics of the traffic system, you collect all that data, you process them, you get what is useful, and you have a traffic controller that generates the control inputs. So you go into this feedback loop. Then I will give you an example of what I mean by that. Let's take a highway where every vehicle transmits its speed, location, OD, and so on. You have a traffic management control center that takes all that information and decides about optimal speed limits, lane changes, route instructions, run metering, and so on. That would be an example of a closed loop system. But I'm going to give you a simpler one. It's too generic. So now, how many of you took a traffic control course here? Traffic. Jeff, have you taught your students traffic principles? Okay.
Yes.
So here we have 5 lanes and the middle lane is blocked. Okay? What do you think is happening here?
All the 5 lanes will be blocked.
Huh?
All the 5 lanes will be blocked.
Why?
Because they're lane changing.
Lane change. So the vehicles here, they don't know that the lane is blocked. They come at 0 speed and they go to the neighboring lanes that are moving 65 miles per hour and they slow them down. What happens at the exit of the bottleneck, you are operating below capacity, well below capacity. Good job. I hope you got an A. So we look at that problem and say, okay, first of all, a lot of people look at that example and they use macroscopic models to figure out variable speed limits and things like that. But the macroscopic model is not going to see the lane changes. It's going to average everything. So what they were getting on was, when they went from the macroscopic to the microscopic, they got very disappointed because they couldn't get the benefits. So what we realized here is, we said, okay, this is the phenomenon. The vehicles are stopping, so you have to let them know to change, give them the control variable becomes the recommendation recommendation to change lanes, and you have to do it ahead of the accident, so that they change lanes where they are at full speed. They don't need to stop. And the question, where do you put the sign? If you put it too close, too late. If you put it too far, you have an empty lane, people will go in. So we found by doing various simulation studies that there is some empirical equation will give you the distance for where you put the sign, and based on this variable, some parameter C, and the demand. It really depends on the demand and the number of lanes that are blocked. So, and here now we put it together. Now, I have to tell you this is a BISIM. If you are familiar with BISIM, this is a microscopic simulator. It's a commercial simulator. There's not much to manipulate here, right? But you can see when we tell them to lane change versus control versus no control. You can see the difference. And it's too intuitive, and it's something that you would expect to see, right? So it's good that the mathematics agree with the simulator and agree with this intuition. And that's what is called good engineering, when everybody's in agreement. If your theory doesn't predict that, then there's something wrong somewhere. So, but the problem here, when I presented this, I said, wait a minute, if I keep pumping more vehicles, you're going to be in trouble in both cases, which is true. So I have to do an additional thing now, because you have here 5 lanes and they are becoming 4 here. So you have bottleneck. So if you increase the flow on the other end that is higher than the capacity of the outlet, you're going to get congestion between, right? I mean, so we ran a lot of experiments with this to see what I described. You see the red is that if you do nothing, right? You get at one point, you get saturated, the capacity of the 4 lanes drop. If you do a lane changing, you get this phenomenon, you get a higher flow, but if you keep increasing the demand, you get this phenomenon. You still move into the congested area, okay? So we have to do something about that too. So, and what do we do in this case in order to protect the network? We do what is called variable speed limit control, which is a lot of people work on it, including ourselves, back 20, 30 years ago, because we thought if there's congestion ahead, there are too many vehicles there, tell the other vehicles to slow down, so slowly we'll clear. And people use microscopic models, claim 20% improvement, including us, and everybody got excited. And then these commercial microscopic simulators came in. And we tried to put it on the microscopic simulator, and not only we're not getting 20% improvement in travel time, it was becoming worse. So people started blaming the microscopic simulators. But the problem was the lane change, okay? So even with the lane change, as I said, if you keep increasing the demand, you're still gonna get. So we decided, and they were using model predictive control and all kind of techniques, but no analysis. So I decided with my student, in fact, that was at the time at IPAM, an arrowhead that we solved the problem. I decided with the student, listen, we got into the transportation, it's a lot of simulation, it's a lot of ad hoc stuff. We need to go back to our culture, which is controls. In controls, we find a model, we develop the controller, we improve stability, we improve convergence, and then we go to simulation. We got to do that. So we sat down a couple of nights and we figured things out. The first analytical proof how things work and why. So the model, so here is your network, right? There's a flow going in and a flow going out. Okay? You don't need to be more than an elementary school to say that your density here will increase if more vehicles are coming in and less vehicles are coming out. So this ordinary differential equation that comes from simple conservation of vehicles, flows, it says that rho dot, the derivative of the density with respect to time, is equal to Q1 minus Q2. So what I like to do, I want this, I don't want the density to increase. So what I is the Q1 to be equal to Q2. So if I put a traffic light here to make sure Q1 becomes equal to Q2 all the time, or a little bit less, then this region will never get congested. But I cannot put traffic lights everywhere. So how do I go from Q1 to speed? So there is a transformation that you go from the flow to the speed, and that's what I'm going to use. Now, this looks very simple, but it's not as simple, because for Q2 to exist, to have a value, it has to be vehicles here. There have to be vehicle available. For Q1 to go in, it has to be a demand, and it has to be a space to go in. So then you create this diagram here that shows what is possible with the input and what is possible with output. And the point they intersect is that equilibrium point. Okay? And then from simple geometry, you calculate the mapping that takes you from Q to this nonlinear fraction, where V is the speed. So basically, we use this to calculate the speed, and we tell the vehicles, this is your speed, and that speed guarantees the flow Q1, which is the one you need in order to not to block the exit. So we look at this particular example and we identify 9 possible situations, and the only situations that will lead to congestion are the first 5, because here the capacities are big. You have plenty of space to go in, so you don't get congestion. So I wanted to look at each case, find the equilibrium point, and design the controller. And here are some of here is the controller basically, which is some PID, if you took any courses in controls, PID, and then we go through, we find the desired flow, and from the desired flow we get the speeds. And we have the main theorem. And the theorem says the system will converge, and it will converge to the one that gives you the maximum possible flow at the exit. Okay? Basically, the whole idea is to not block the exit. The exit are 4 lanes open. These 4 lanes should reach capacity. And the only way to reach capacity is to make sure there is no congestion between. Okay? So this is the first proof that will go. Everything was clear with our equations, but here I show you something that is clear to see the open loop and the closed loop. So the open loop system here, where you're there are 2 equilibrium points. One equilibrium point is a congestion, and the other one is not congested. So depending where the intersection, where that region, what kind of density it had initially. Here, no matter where it is, it will always converge to the non-congested equilibrium. That's for a particular demand. Now, if I increase the demand, you still get the same situation, but the open loop can give you a lower capacity, a lower flow, and be congested, depending on initial conditions, whereas the closed loop will always give you the best possible flow. Now, if you go to this case, now the open loop will have only one equilibrium point, and that's a congested equilibrium point, whereas the closed loop is going to go to the maximum possible.